Morning, everyone. Welcome back to another exciting day in mathematics. Whoop, whoop. Warm up 87 should come up on your screen. Let's get started, please. You will need a calculator. Morning. Make sure you grab a calculator and a gopher. Give you guys some time. Copy and go. All right, pretty good. Get us started, please. Mean. How about Mario? What'd you get for the mean? Is Mario here? 18? Yeah. Hands if you got that. Looks about right. I need a standard deviation. Pass someone. Max, what'd you get for standard deviation? $14.8. I'll leave it at 14.8. That is about right. So this is at 32.8 or at 3.2. That's the norm from 3.2 to 32.8. All right, now we need a z-score for the number 24. Number 24. All right, pass on one, Cord. All right, Max. Z-score for 24, now that you have the mean, now that you have that number, and now you have the standard deviation, you should be able to use that in the formula. All right, pretty good. Vianney. Oh my goodness. 0.40 or 0.4 looks about right. So from the mean, we go to the right almost halfway, so about right there, 0.4. All right, pretty good. Let's go to the compute 3 factorial divided by 5 factorial. Passing one, Brandon Doherty. Mel, what'd you get? 0.05. Or in other words, we can do 3 factorial over 5 factorial, which is 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. That leaves us on the numerator with 1. Denominator 5 times 4 is 20. If you divide that, it gives us 0.05. All right. Pretty good. Copy the agenda. Then I'll send you the screen so you can send me your warm-up. All right. Copy the code to access the home plate tonight. Only 8 problems. TN 75A. TN 75A. Now, on a side note, as I mentioned last week, this week's going to get warm. Next week's going to get warmer. We're going to be in the 90s already. What? Already in February? What? But anywho, we'll still have the winds coming for the fair, right? Can't have a fair without the winds. So, anyways, 8 counting rule problems for tonight. Get a Cornell note ready, please. And our objective for today, I can identify and compute problems with the fundamental counting rule. I can identify and compute problems with the fundamental counting rule. Now today I'm going to introduce 2 rules, but one of them, which is the fundamental counting rule, I'm going to show you how it's used. We're going to do like 2 or 3 problems with the rule, and you are going to come up with the actual rule by yourself. You should be able to do that just by looking at the process that we do. Okay? Here goes our roadmap where we've been. We talked about probability and the definition of probability. with the three different types of probabilities that we've been talking about? Yes, we are experts at that by now. But that drops us now to what we call counting rules. So we've done a lot of probability with coins, with dice, with cards. But now we're going to get into more of the trying to stay away from actually doing the exercise or the experience. So like that, we can just use rules to get us through the entire problem of finding how many total outcomes for an event or a problem with several events. So this is where we're going. Today we're going to focus on fundamental counting rules. However, from there we're going to move on to permutation rule. And then towards the end we're going to be in the combination rule. Now, this is the roadmap. This is where we're headed. Today we're going to focus on the first one. Now, I can tell you this, all these rules are used almost on a day-to-day with different types of problems that are arising from the workplace. And also, some of you or some of your parents that buy lotto tickets, they're going to find that these two last rules, permutation and combination, could be used to find out how many total possible outcomes you can get from the lotto. But anyways, we'll get to that as soon as we are done with the others. So, with that said, copy this one on your paper, please. Example 1 reads, a coin is tossed and a die is rolled. Find the number of outcomes for the sequence of events. All right. And then, once you copy that, copy this tree diagram, please. And then I'll send that to your screen. All right. So, this problem we've already done like a couple of times in the past. Is that correct? Does it look familiar? Yes, Mr. Q. The coin tossed and the die rolled. Okay. Then we did a tree diagram from that as well and all that. You have the notes for that. And just to double check, look up, these are the outcomes right here. Is that correct? How many total outcomes? 12. Okay. However, look up, please. The counting rule we've been using with these problems, we've used it before, and here it goes. Look up. Coin, die. So, tell your neighbor how we get this without having to do a tree diagram. Talk it over your neighbor. How do we get the total outcomes without having to sketch a tree diagram? What do we do? Tell your neighbor, what do we do? Looks like Carter's got it. Very good, Carter. And just FYI, once again, this is being recorded, all right? Just giving you a heads up. All right, how do we get that? Austin, T, go. Without sketching a tree diagram, how do we get 12? Multiply what? Amount for the die and the amount for the coin. So it would be, the coin would be how many? 2, and the die, and that gives us, yes, and this is what we call the fundamental counting rule. That's when you find the total outcomes without actually sketching anything or actually going through the through a table or anything like that. Okay. So, what if I gave you something that looked like this? All right, let me zoom in. I'll zoom into the problem because, once again, we're using the fundamental counting rule, in order to avoid making these huge diagrams. Is that correct? So, it reads, there are 4 blood types, A, B, AB, and O. Blood can also be Rh positive and Rh negative. Finally, a blood donor can be classified as either male or female. How many different ways can a donor have his or her blood labeled? So on your paper, I want you to write example 2, copy the question, and then give me an answer, but show me work without having to do this diagram. As a matter of fact, let me cover this up. How many different ways can a donor have his or her blood labeled? All right, let's see. Amelia. Amelia, what did you do to find the total answer? You multiplied 4 times what? Times 2? Times 2. And that gave you 16. Hands, if you got that? That is correct. 4 blood types. 2 more blood types. And the classification of 2. So that gives us 4 times 2 times 2. That is 16. Send that in, please. And once again, this is, did I send you the screen already? Yeah, right? This is the fundamental counting rule. So think about it. Because right now, one of you is going to actually give me the rule just by what you are doing right now. You should know the rule. All right, let's move on. Example 3 on your paper. Copy the question. How many different kinds of paint can be made if you can select one color, one type, one texture, and one use? Copy the question, please. And let me read you the entire problem. Example 3 reads, bless you. A paint manufacturer, bless you, wishes to manufacture several different paints. The categories include color. What colors are available? Red, blue, white, black, green, brown, and yellow. Type of paint. What type are there? Latex and oil. Texture. Flat, semi-gloss, high gloss. And use. Outdoor or indoor. So, copy the question. Find the total or how many different kinds of paint can be made. Go. All right. So Amelia's going to pass it to someone, and I don't want you to give me the answer only. I want you to tell me the process. What did you do? All right. So Amelia, pass someone. Logan, what'd you do? So you said 6 times 2 times 3 times 2? Okay, where'd you get the 6 from? 7, okay. 7. And multiply them all. So therefore, 2 times 3 is 6, times 2 is 12, times 7, 84. Hands, have you got that? That is correct. That is correct. So, walk me through the process one more time, Logan. Where'd you get 7 from? The number of different colors. So you looked at the data and you labeled it. That was 7. Okay, and then? Type. 3. and use. Okay. All right. From 1 to 5, I'll come through. Are you with this? Yeah, we got it, right? Okay. Last one. Here we go. Copy the question. Example 4. How many different cards can be made if she uses the digits 1, 2, 3, 4, 5, and 6, and repetitions are permitted? Repetitions are permitted. And let me read the problem now as you're copying the question. The manager of the department store chain wishes to make a 4-digit ID card for her employees. So let's sketch an ID card over here on the side. Try your best. I know some of you are artistically challenged. Just try your best. Here's the photo ID. All right. And over here on the side, we need how many? It says how many cards can be made if she uses digits 1, 2, 3, 4, 5, 6. And it's a what? 4-digit ID card. 4 digits. So over here on the corner, I'm going to put the 4 digits. Digit 1, 2, 3, and 4. All right. Talk it over to your neighbor. Let them know what are we going to use from that information. Then Austin T is going to enlighten us with this part. I'll give you guys some time. Go. All right. Austin T, total number. Well, let's go one step at a time. How many different digits can fit on the first slot? 6, okay. Then it says repetitions are permitted. So how many on the next one? And the next one? Therefore, if we use the fundamental counting rule, how many total different cards can be made? Pass someone? Max, total number of cards, different cards. What do we need to do now that we know how many digits in each slot? Multiply 6 times 6 times 6 times 6, and that gives us a total of 1296. Hands, have you got that? That is correct. Send that in, please. Send me your work. All right. Thank you, guys. So, what we just experienced is called the fundamental counting rule. Write that on your paper, please. Fundamental counting rule. What you just experienced is called the fundamental counting rule. So the rule has 2 steps. Talk to your neighbor, let them know what is the 2 things that we did to come up with that number at the end. What are the 2 things that we would do? What would we do to find that number? All right. Looks like Austin's got this. Austin S., what is the first thing you did? look for all the data in the problem. That is correct. And once we looked at all the data, what did we do with that data, people? Everyone. What did we do with that data? Multiply. Multiply all outcomes for each event. And that's how we get our answer at the end. Now let me give you a rule in actual with formula setting. It looks like this. K sub 1 times K sub 2 times K sub 3 dot dot dot, and you continue going to K sub n, which means basically multiply all the different outcomes for all the different events, and that's how you get your answer. For 1 to 5, I'll come to borrow you with fundamental counting rule. Okay, right? 5? Yeah. However, we got 2 more rules to write down. Here we go. Write these down. Factorial formulas. Let me zoom in. Factorial formulas. For any counting n, the first formula is n factorial, which equals n times n minus 1 times n minus 2 dot 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 till you get to 1. Now if you want to put that into numbers, let's say n is 7. So 7 factorial is the same as 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what this formula means. The second one, it is a formula, but it's more like a rule. Whenever you see 0 factorial, that is equal to what? 1. 0 factorial is equal to 1. 0 factorial equal to 1. We good, Max? Yeah? How to go with the car wash yesterday? Good? Yeah? Car wash? Yeah? I was going to stop so you can help me, but I said, nah, he's got his hands full. All right. So with that said, copy the question, please. Example 5. Example 5 reads, the manager of department store chain wishes to make 4-digit ID cards for her employees. How many different cards can be made if she uses the digits 1, 2, 3, 4, 5, 6, and repetitions are not permitted? Very similar to the one we just did earlier, but this one, repetitions are what? Not permitted. So, copy the question, please, only. I'm going to sketch over here the ID. And once again, 4 digits. Digit 1, 2, 3, 4. All right, as you're writing that down, let me recap what Austin T. walked us through earlier. He said, well, Mr. Q, I can use 6 numbers for the first slot, 6 numbers for the second slot, third and fourth, but because it said repetitions were permitted. Is that correct? However, in this one it says repetitions are not permitted. So talk it over to your neighbor, let them know what possibilities do we have here. Talk it over to your neighbor, please. All right, walk us through this. Who went last? Austin S? Pass someone, Austin. Kieran, how many possible numbers on the first slot? 6. How about the second one? How about the third one? And the fourth one? Does this look familiar, guys? That is almost what? 6 factorial, is that correct? All we need is 2 and 1, but we're not going to use these because we only have 4 digits. So therefore, 6 times 5 times 4 times 3, that gives us 360. And have you got that? Yeah, we got it. From 1 to 5, how come are you using factorials for this? Yeah, we got it, right? We just need to apply it to a problem. All right, so I'm going to stop the video right there, and I'm going to give you guys a head start for your home play right now. I'll send it to your screen. Also, those of you that are following along on YouTube, you have the code. Go in and do the practice. It's only 8 problems, and I'll see you guys next time. Peace.